Echelon form. A matrix is in row echelon form if it satisfies three conditions. I'm going to go through them one at a time. The first condition is that the leading entry of each non-zero row after the first occurs to the right of the leading entry in the previous row. Let's look at an example of this first condition. So here we have a matrix 0, 3, 1, 2, 4, 7. Notice that the leading entry in the first row is this 3, and the leading entry in the second row is 2. The leading entry in the second row is to the left of the leading entry in the first row, and therefore this first condition is violated. So this matrix is not in row echelon form. We could put it into row echelon form pretty easily by interchanging the two rows. So let's go ahead and do that so that we get the matrix 2, 4, 7, 0, 3, 1. Notice that the leading entry in the first row is now this 2. The leading entry in the second row is this 3. And this now satisfies that first condition because the leading entry in the second row is to the right of the leading entry in the first row. First matrix was not in row echelon form, and the second matrix is in row echelon form. At least it satisfies that first condition. The second condition is that all entries in a column below a leading entry are zeros. So let's look at another example. Here we have the leading entry in the first row is 1, and the entry below it is not 0. So condition 2 is being violated here, and therefore this matrix is not in row echelon form. We can fix this by doing a row replacement operation. We'll do row 2 minus 2 row 1. So we rewrite the first row, 1, -3, -3, because that row is not changing. We've done this before, so I'll go through it a little quicker this time, column by column. From the first column, we have 2 minus 2 times 1 equals 2 minus 2, which is 0. For the second column, we have 1 minus 2 times -3 is 1 plus 6, which is 7. And for the third column, we have 8 minus 2 times -3 is 8 plus 6, which is 14. This first matrix is not in row echelon form. The second one is. The third condition is that all 0 rows are at the bottom of the matrix. So here's an example of a matrix with a row of zeros. You can see that second row is all 0. This violates condition 3 of the definition for being in row echelon form, and therefore this matrix is not in row echelon form. But we could fix this pretty easily by interchanging the second and third rows. We now get a matrix which is in row echelon form. First one is not, second one is. Notice that the leading entries in this second matrix go from left to right as we go from row to row, and all the entries below the two leading entries are all 0, showing us that conditions 1 and 2 are also satisfied. Okay, let's look at some examples of matrices that are in row echelon form. This matrix, 1, 2, 3, 0, 3, 6, notice that the leading entries are 1 and 3. They move from left to right as we go from row to row. The second row has a leading entry to the right of the leading entry in the first row. The corresponding system of equations is x plus 2y equals 3, 3y equals 6. Now, matrices that are in row echelon form, their corresponding systems of equations are pretty easy to solve. We could do it by back solving. From the second equation, we can divide each side by 3 to get y equals 2. And now let's look at the first equation. We subtract 2y from each side to get x equals 3 minus 2y. We can replace y by 2 to get 3 minus 2 times 2, which is 3 minus 4, or -1. So we see that -1, 2 is the only solution to this system of equations. Another example, 2, 3, 5, 0, 0, 4. The leading entry in the first row is 2, and the leading entry in the second row is 4. Notice that the conditions of being in row echelon form are satisfied. Let's write the corresponding system of equations. 2x plus 3y equals 5, 0 equals 4. This second equation, 0 equals 4, is simply not true, therefore a contradiction. I use that lightning bolt symbol again for a contradiction, and that indicates that this system of equations has no solutions. In fact, it's a general theorem that if the last column of an augmented matrix of a linear system in echelon form contains a leading entry, then the system is inconsistent. In this example, the number 4 is a leading entry in that last column, leading to the system of equations having no solutions. Another example, 179,000. Only one leading entry here in the first row of 1. The corresponding system of equations is x plus 7y equals 9, 0 equals 0. Now that second equation, although it's true, it provides no useful information, so we could simply disregard it. And in general, rows of zeros can be disregarded. Let's go ahead and solve that first equation for x to get x equals 9 minus 7y. The general solution of this system of equations is x equals 9 minus 7y, where y is free. What we mean by y being free is that we can replace y by any number we want, and we get a corresponding value for x, leading to some solution x comma y. In other words, this system of equations has infinitely many solutions, one for each choice of the free variable y. This solution, the way we've written it, is called a parametric description of the solution set. Let's look at this matrix again, 179,000, and let's note that the first two columns correspond to the variables x and y in the system. So looking at the first column x, we see that it has a leading entry of 1. Since the column corresponding to x has a leading entry, we call x a basic variable. A leading entry is also called a pivot, and a column with a pivot is called a pivot column. So the column corresponding to x, or the first column, is a pivot column, and the leading entry of 1 is called a pivot. Let's look at the second column. Since the column corresponding to y does not have a leading entry, y is called a free variable. So this column is not a pivot column. Another example. So the leading entries in this matrix are 1, 2, and 3. Notice how they move from left to right as we go from row to row. And below all the leading entries, we have all zeros. The columns correspond to, let's say, the variables x, y, and z. And all three of those columns are pivot columns because there are pivots in each of those columns. The pivots are 1 in the first column, 2 in the second column, and 3 in the third column. X, y, and z here are all basic variables. The corresponding system of equations here is pretty easy to solve using back solving. We can divide the last equation by 3 to get z equals 4. In the second equation, we subtract 5z to get 2y equals 8 minus 5z. Substitute in a 4 for z to get 8 minus 5 times 4, which is 8 minus 20, or negative 16. Finally, we divide each side of this equation by 2 to get y equals negative 8. Now, the first equation, we can get x by itself. We have x equals 2 minus y minus z. Substitute in a 4 for z and a negative 8 for y to get 2 minus negative 8 minus 4, which is 2 plus 8 minus 4, or 6. So we see that x equals 6, y equals negative 8, z equals 4 is the only solution to the system of equations. One more example. Okay, this matrix, we see the leading entries of 1s move nicely from left to right as we go downward among the rows. And below each leading entry, there are only zeros. And the last row of zeros is okay because all the 0 rows are at the bottom of the matrix. Notice that if we let the variables be x1, x2, x3, x4, and x5, then the pivot columns correspond to variables x1, x3, and x5. The pivots are the corresponding entries of 1, 1, and 1 in those columns. x1, x3, and x5 are basic variables because they correspond to pivot columns, and x2 and x4 are free variables because those columns are not pivot columns. The corresponding system of equations here is x1 plus x2 plus 2x3 plus 4x4 plus 5x5 equals 7, x3 plus 2x4 equals 1, and x5 equals 3. We're going to go ahead and solve for the basic variables. The last equation, x5 equals 3, is already done. The second equation, we subtract 2x4 to get x3 equals 1 minus 2x4. Since x4 is a free variable, we'll leave it just like that. From the first equation, we have x1 is 7 minus x2 minus 2x3 minus 4x4 minus 5x5. We'll go ahead and replace the basic variables x3 and x5 by 3 and 1 minus 2x4 respectively. And then we'll distribute that negative 2 to get negative 2 plus 4x4, and we'll multiply the 5 times 3 to get negative 15. When we add all the constants, 7, negative 2, and negative 15, we get negative 10. Notice that the 4x4 cancels with the negative 4x4, and there's also a minus x2 there. Okay, so we have the three basic variables, x1, x3, and x5 here. x1 is negative 10 minus x2, x3 is 1 minus 2x4, x5 is equal to 3, and x2 and x4 are free variables.